Bismillah Rahman Rahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Dear students, we saw that in our previous videos that we actually have a scanner, or what we call as a lexical analyzer, and out of the output of this is the tokens, and these tokens are given to the parser or syntax analyzer, which actually try to say whether these tokens are valid or not. Now question arises, how parser actually tell us that these tokens are valid tokens or invalid tokens, right? Now I know not all sequencer tokens are programmed, and parser must distinguish between the valid and invalid sequence of tokens. That is the important thing which a parser does, and we need some sort of an expressive way to describe the syntax. And we also need an acceptor mechanism that determines if input token stream satisfies the syntax or not. So this is where the grammar comes into the play. So for the expressive way which we're talking about to describe the syntax, we will need a mathematical model of a syntax. That is a grammar. We'll talk about it in detail. And the acceptor mechanism that determines if the input token stream satisfies syntax. For that we need algorithm for testing membership in a language pertaining to this grammar. It was way back actually a Norwegian mathematician Axel II who studied the sequence of binary symbols subject to interesting mathematical properties, such as not having the same substring 3 times in a row. His work actually influenced Emil Post, Stefan Klein, and many others. What they do is they start studying the mathematical properties of strings and collection of strings. Then soon, when we see the modern computers, people realize that all form information, whether numbers, names, pictures, or sound waves, can be represented as strings. That's the point. And then collection of strings known as languages became central to the computer science. This thing actually revolutionized the computer science and the language formations and a lot of things. It was actually in late 1950s linguistic and Chomsky proposed a mathematical model for grammars of natural languages. We are talking about that we need a mathematical model, when he attempted to actually give a precise characterization of the structure of natural languages. His goal was to define the syntax of language using simple and precise mathematical rules. Okay, actually it was his attempts were for the natural language, but it didn't work for natural language. But it worked for the computer languages. And in 1956, it was found that the syntax of programming languages can be described using one of the Chomsky's grammatical model, which is called as the context-free grammars. Now, a context-free grammar is a 4-tuple, which is consisting of a S for the start symbol, N for the non-terminals, T is the set of terminals, and P is set of productions. So let us discuss all these things in detail and take an example to see what these are. Firstly, we should note that the context-free grammar is a formal grammar, and why we call it a context-free grammar also is because it is a formal grammar. The formal grammar means which talks about the form. Okay, it doesn't talk about the semantics. Okay, a formal grammar is when the context is not given. We call that as a formal grammar when we don't have a context or semantics. So when the semantics is not there, we have a formal. That's we're talking about only about the form. Okay. So it's actually a set of these production rules. The productions are actually the rules. The grammar is actually all about the production rules for strings in a formal language. Okay. Now what this rule does is they tell us how to form strings from the language's alphabets that are valid according to the language's syntax. Okay. What I mean to say, for example, we have an alphabet and we start. We know we can have an if statement and so on, an expression here. And if I'm writing, say for example, fi now, the grammar will tell us how to form a string from the language is alphabets. So we have I and F in the language alphabet, okay, and we can form a string either if or fi. So the grammar will tell us that both of these guys are correct syntax, if we talk about the syntax. So syntactically they are all, both of them are correct, right? Now semantically fi will be wrong, okay, so that's not the consideration of the formal grammar, or what we call the context-free grammar, where we don't talk about the semantics, we just talk about the syntax, the form. That's why we call them as a formal grammar in the first place. Do you understand this thing? For the detailed discussion of grammars, you should watch my video on the types of grammars in the automata videos. Okay. Now let's take an example. Say for example we want to represent a language. We have a language. Say for example, as a pen, language of palindromes. Now we all know the palindromes, okay? Let's call it L of P. Okay, a palindrome is a string that reads the same forward and backward. For example, we got the madam, isn't it? For example, if I say 0, 1, 0 or something like that, even if we have the epsilon, that's also the palindrome, or we may have the 0 or we may have the 1, they are also palindrome because you read it left to right or right to left, it will give the same meaning. So for example, we got an input symbol here of 0 and 1, and we wanna have a palindrome, a language of palindrome, and we know there is a natural recursive definition when a string of 0 and 1 happens to be in the palindrome. So what I do is we need to have two things, one is the basis and one is the induction. So in a basis we say if we have an epsilon or we have a 0 or we have 1, they are palindrome, right? Because they are single characters, not a problem, and epsilon is nothing, so that's also a palindrome. Then we have an induction, okay, and induction does what? We say if w is some string, w is a palindrome, so we already have seen the w is a palindrome. Then if we say 0 w0 or we say 1 w1, okay, they are also palindromes. Okay, if w is palindrome, any string that is a palindrome, and we put up a 0 in the beginning and the end, and here also 1 in the beginning and the end, they are also palindromes. So we say it will not be palindrome unless you don't follow the basis and induction, right? Now the languages like these which have the recursive definitions, the context-free grammar is a formal notation for expressing such languages, right? So this is where our regular expression fails, okay, because we can't count in the regular expressions. We have discussed that in a video 1, and here I'm telling you again that context-free grammar is a more powerful grammar which will take up these cases. And we come to with this example we come to this formal definition of context-free grammar here. What is the star symbol, non-terminal, terminal, and productions? So if we want to have a grammar for the palindromes, we need to follow the basis and the induction. We have to keep it in the mind, right? So we may have some rules to build our this language. We may have, we say the first is the P, maybe we call it the P. So this is one variable which represents the set of palindromes, okay? So we have a class of strings forming the language. So L of P, for example. So I say P will first have the epsilon, or P may have the 0, or P may have the 1. These three rules are actually the induction, the basis, right? They are simply the basis what we're talking about. So we say that the class of palindrome consists of or includes epsilon, 0 and 1. Now they form the basis because on the right side of these expressions we saw in this rule contains there is no variable in it. Okay, so that's what we call in the basis. But we need to have the induction part also here. So we say like this, we say here p 0 p0. That means if we have some string here which is already the palindrome, then if we add 0 0, that's again be a palindrome, or same way 1 p1, right? So these last two rules forms the induction part of the definition, right? Now if we come back to the formal definition of context-free grammar, we saw that we have the T. Let's talk first the set of terminals. Okay, now these terminals are actually the basic symbols from which strings are formed. Like what comes out of the out of the scanner, right, is the tokens. These tokens are actually the terminals, right? So in this case of the rules we saw here, the epsilon, the 0, the 1, these are the terminals. In many cases we may have like the ifs, else's, the parentheses, whatever the tokens are. Okay, they are the terminals. And then we have the non-terminals which are called as the syntactic variables. They are also called the variables, like here the p. Okay, that actually denote the set of strings. Now these set of strings actually denote the non-terminals okay, that help define the language generated by the grammar. Now we may have the production rules. So like here we saw the rules. These are the production rules which we talk about here. The P is a set of productions or rules. These are actually the rules. The production of the grammar specifies the manner in which the terminals and non-terminals can be combined. They will tell us how to combine the terminals or the non-terminals. Okay. Now on the left side of this production rule we have a non-terminal. Okay, and on the right then we have an arrow. Okay, sometimes we may have sometimes we may have like this, the double colon and equal to, or we may have an arrow sign for the production rule. Okay, now on the right side we may have 0 or more terminals and also the non-terminals, right? Like here we saw the terminals, and in this rule we saw terminal as well as the non-terminal. It can be a combination of many terminals and non-terminals, but on the left side we always have a non-terminal. Now if you look at this, this is a grammar for the simple arithmetic expression. Okay, and the terminal symbols in it, if we see, are the ID. Okay, it could be the parentheses itself, it could be the star, it could be slash, that was divide, or plus or minus. These are actually the terminal symbols. Okay, the rest of the guys are non-terminals or variables. And the start symbol is going to be the expression, right? The expression is the start symbol. And the non-terminal symbols are all of these guys, like a term, like factor. And on the left side we always see that there is a non-terminal, and on the right side is the combination of, say, from the expression and term, the non-terminals, and plus is a terminal, combination of these. Okay, the term itself could be term into factor, or term slash factor, or it could be the factor itself. And the factor is simply an expression in the parentheses, and factor can also be the ID. Okay, the ID can be the actual number. Now every time we try to figure out which is terminal or non-terminal, we got actually the notational conventions, where we see that if you want to talk about terminal, if you have lowercase letters like A, B, C somewhere, they are actually terminals. If there are operators in this example, say plus, minus, and so on, they are also the terminals. And there are punctuation symbols, such as parentheses, comma, and so on. They're also, like, the parentheses are there, they are terminals. And if it's a digit 0 to 9, they are terminals. And if they're bold faces like ID, we make it a bold, or if or whatever, then make it a bold, and that they are terminals. Now these symbols are non-terminals, like where uppercase letters A, B, C, like we had P in this case, is a non-terminal, right? The uppercase. The letter S, which when it appears, is usually the start symbol. Okay, if not necessarily, if you have an expression here, this is our start symbol, but many times we say S as a start symbol. And if it's a lowercase italic names like exp or statement stmt, we say so lowercase and italic. That's important. And in the case there's a bold face, okay, then we say they are terminals. And non-terminals, expression statements. But what I mean to say is italic names. When discussing programming constructs, uppercase letters may be used to represent non-terminals, like we said here. Okay, so for example, we have a term, we can say T for it, factor F, right, and so on. Expression E, capital E. If it's caps, then it is a non-terminal. If it is small letters, it is a terminal. Okay, and in these cases, italic versus bold. Now if we try to rewrite these expression, grammar for simple arithmetic expression using these rules, we may say firstly here, maybe I call it an E, okay, that it gives, we have E plus term, T for term, or I could write it here or here, or E minus T, that is this guy, or simply the term. Okay, after this thing. Now the term itself, T, is either the T into the F factor, right, or we have T slash factor, that is this guy, or we have simply the factor, right? Now whatever the factor is the third thing. Factor is the expression in the parentheses or ID. Okay, now it has to be bold face. I will make it like a board like this, right? Okay, ID. Now if we see here, they are all capital. The capital guys, as we know, are the non-terminals, and the bold faces or parentheses or pluses and minuses, they are terminals, and E is gonna be our start symbol, right? Okay, now let's take up another example of balanced parentheses. Okay, so we have here the non-terminal variables. Let it be the S, okay, and terminal be the opening and closing parentheses. And then the production rules, start symbol will again be the S, start symbol will be the S, okay. And the production rules, what we have, production rules we have is S derives in appearances S and or epsilon, right? So what we say is the S can be derived as the parentheses of S and epsilon. So for example, we have a one parenthesis, so we can use a rule number 1, which says by using rule number 1, say this is rule number 1, and let it be rule number 2. Okay, let it be rule number 2. So applying 1, what we do is we say S after deriving this thing using this production rule. Now we will make the second rule. Now S derives epsilon, so this is epsilon, so this will applying second, so this is gone, so it will be like this. Okay, now we may have more these things like for example, we have the parentheses like 2 parentheses, right? So we say firstly that use the rule number first, which says S. Okay, now again use the rule number for this S. Now we use the rule number first again. So this is again for this S, we use the rule number first, and then rule number second, this S goes to epsilon. So we have this thing. So we by using the induction, we can have the many parentheses, right? Now let us see the next example. We see the CFG for, say, we have 0 raised power n and 1 raised power n. That means we have the same number of zeros and ones, and n is greater than or equal to 1. Okay, so that means you have at least 1 0 and 1. If you have a 1 0, you also need to have a 1 1. Okay, if you have 2 zeros, then 2 ones, 3 zeros and 3 ones, and so on. So the simple the basis, and if you say basis and induction, because we say always we have the basis and we have the induction. Okay, basis will be that we have at least 0 1, right? So 0 1 need to be there in the language, and then the induction says that you have 0 w1, that you have any string w in the language, then 0 w1 is also the pertaining to this grammar, right? So what are the production rules? If we say our terminals, they are gonna be what? They are gonna be 0 and 1, right? What about the non-terminals or variables? Let it be the S, okay, which is our start symbol as well. Start symbol is also the S, okay. And what's left out? What is the left of the production rules? Now the production rules. Now we have the first production rules which says induction, that is 0 1 need to be there. Then the basis. Then the second production rule will be the induction, that is 0 S 1. Okay, I'm using the S here, so 0 S 1. This is my by the induction, right? So now if I have for example a string which has 1 0 and 1 1, I can use the S only, right? Now what is S? You're using the induction rule 0 1. The S is 0 1, so I can say it is 0 1. Okay, and we are done. Maybe I have another thing, like we have, say for example, we have a couple of zeros and couple of ones, right? So what I do is I use firstly the S, so the start symbol, because I have to use the start symbol first. Okay, the start symbol, I use the derivation first, so it's the rule 1, and this is the rule 2. So I will use the rule 1. Rule 1 says S goes to 0 1, but then it will stop, so I have to use rule second, which says 0 S and 1. So 0 S and 1 by the rule second. Okay, by rule second. Now here this S, I will use the rule 1 to convert S to the 0 1. So I will derive it, say 0, and this, for this S I will say 0 1 and this 1. Now I got a couple 0 and couple 1s. The same way I can do any many zeros and any many 1s, right? Now let's take a little more, same example, a little complicated, that it says that we need a context-free grammar, for example, for language equals to 0 raised power m and 1 raised power n, so that m is greater than or equal to n. Okay, so now we have not same zeros and same ones. It can be either same 0 and 1s, or zeros may be more, because m is greater than or equal to n. So what will be our grammar for this? So we know the terminal symbols and all. We have t equals to 0 and 1, right? Okay, now variables, we may have a couple of variables here. Let me write the first production rules of the grammar here. So I say S, firstly the start symbol, that derives what? I will say firstly it is the 0 S 1, okay, or I will say it will go to A. Then A, I will say goes to 0A or epsilon. Now this is my grammar rules. So I have the couple of variables here, that is S and A are my variables, right? Okay, and start symbol is S. From these variables, one of the variables have to be start symbol, that is S, and the production rules are here, which says 0 S1, then I say A, then 0A or epsilon. What does that mean? So for example, I want to derive, I have a string which has 0 1 only, because I can have same number of zeros and same number of ones if m is equal to n here, right? So what I do is I will use which rule I will use for this. So definitely I'm gonna use the first rule. I have to use this s, and when I derive the s, that is equal to 0, s, and 1. Okay, now what is this s here? I will use this one, the rule number second. I will make the s as an a, derive it as an a, 0, a1. Now I will use a I have to derive now a. Now after a I can use 0a or epsilon, so I will use epsilon here, right? So this becomes 0 1, right? Or I could have, say for example, I have a couple of zeros and 1. What will you do for this? So firstly you will use an s. Now s is here, right? So you can use a 0s1, 0 s and 1. Okay, now here this s, I have to do s. Now I use a rule second, that is a, s goes to a. So now here s goes to a. So what will happen here, excuse me, where is my pen? Okay, now s goes to a, 0 a 1. Now this a will use the rule number third, this is this guy, 0 a this time. Okay, now I will use it, this a goes to 0a, right? So 0a and 1. Now this a using rule number 4 goes to epsilon, so this is 0 0, this a goes to epsilons, right? So this epsilon is gone, so it is 0 0 1, so I got the string 0 0 1. Okay, now let us talk about three things. One is the derivation, one is the sentential form, and another one is the parse tree. So what is a derivation basically? Now a derivation is a sequence of productions. Okay, what we did here, we tried from a start symbol, and we did some sequence of productions to arrive at some strings. For example, this thing in these examples which we discussed, and the derivation actually is these sequence of productions. Okay, and now these derivation can be drawn as a tree, and that tree is called a parse tree. Okay, we will talk about this in a moment. And now then we have what's called a sentential form. So a sentential form is actually any string derivable from the start symbol. That's what we did here. So we had start symbol, then we have this, then this, then this. These are all what we call as the sentential forms, right? And then we have what's called as a sentence. One more thing here is a sentence. The sentence is actually a sentential form, okay, consisting only of terminals. So when we are talking about only terminals, we don't have any variables out here, then that thing is a sentence. Okay, now because we are talking about the parser, it's actually a program that determines if a string, say for example W, belongs to some language with some grammar G or not, by constructing a derivation. So this is what a parser does actually. It has a production rules as per the context-free grammar. Okay, it has the derivations. Okay, and it creates out of these derivations a parse tree, and the parse tree at the end has a sentence. Okay, when everything is derived, we have a sentence on the bottom in the leaves, which actually is the token. Okay, which wherein we have the terminals. Okay, and then that string, if we could draw a parse tree of that string, and we find that yeah, string is there, so that means the strings belongs to the that language or put into that grammar. If we couldn't, we say that there is a problem with that string, right? So what exactly is the parse tree then? A parse tree is a graphical representation of derivations. So like we did here, the derivations we did, and it's graphical. We now represent this graphically, okay, of these derivations. I mean derivations sequence of what? because they are derivation sequence, because I say, hey, I do this derivation, then like I said, rule 1 or rule 2 or rule 3. So these are the actually the production rules, and these are the derivations, and I use the derivation sequence, okay, of this form. What is the form called? Sentential form, right? So parse tree is nothing but a graphic representation of the derivation sequence, or these rules, sequence of these rules, and what we have is actually the sentential form. So derivation sequence of a sentential form. So a parse tree is actually nothing. If we say a parse tree, it is same as saying as a derivation tree, right? Because it is the derivation sequence of these sentential forms which actually tell us what the parse tree is. Okay, a parse tree is some sort of which has a node root, okay, and then it has a nodes, then it goes from this node to that node and so on. It can do that. We'll see that in an example. And these tree nodes represent symbols of the grammar. Now they can be the terminals or non-terminals, right? And these edges, okay, represent the derivation steps. So these are your derivation steps, and these nodes are either terminals or the variables, or what it says, the non-terminals. Let's take an example to understand the derivations and the parse tree and whatever I'm talking about. So for example, we've got a grammar G, which is okay, when we have that expression E, either it could be E plus E, or it can be E star E, right? Or it can be in appearances E only, or it can be the actual ID, right? This is my grammar. And say I have a string, say for example I got an ID into ID plus ID, right? Whatever it is, A into B plus C, for example, we have. Okay, now I'm saying in general ID. Now I want to see whether the string is belonging to the language pertaining to this grammar or not. Say this is my W, okay, and is W belongs to L of G or not, right? So what I do is, if I could make a parse tree out of it, if I could derive this string from this grammar and make a parse tree of that, if the parse tree exists of this string, then yep, that belongs to the grammar. So I can say, yeah, this is correct. Okay, so how I do that? Now here the parse tree will also tell us the precedence. Okay, I'm not going to detail of that, but just see, the show you will tell you when I start making it. Okay, so I have to use out of these rules some rules. Say for example I use my first rule that E goes, I have to start from some start symbol, right? Let me do it here. Let me use a start symbol here, say E. Let me start writing. Let me change my pen firstly. Let me write in red. Okay, so I will choose an E. Now in a parse tree I have a root, the start symbol E. Then I choose some rule. So from the derivation I have to use some rule, right? Maybe I will use the E plus E, the first rule for this E. Okay, so I'm using a rule E plus E. So I use a rule what is called as E plus E, okay, in this. Now here, because I am using E in a tree, I have the start symbol, and then I have its children, 3 children. One is the E, one is a plus, another is the E. Okay, and again a sentential form. And this sentential form elements actually becomes the children of the root. Okay, now I may use I have to derive again. I may actually derive this E, or I may derive this E. Okay, whatever you like. So that means I can go from the left or I can go from the right. That is why your parse tree can be left derived or right derived. We'll talk about this in a moment. Okay, so say for example here I will take it from the left, and I this time use the rule number this e asterisk e for deriving this e, right? So what I do is I will derive this e as e plus e asterisk e, and this one remains there. That means I chose here this e to expand this e to e asterisk and e as the three children of this. So I'm building my parse tree. Okay. Well, I'm using my leftmost derivation, so I go expanding this e, the leftmost, and let me use now this rule. Say for example this id rule. Okay, rule number last. So I make this e into the id. Now I convert this e into id. Now this goes here, this goes here. Now what will happen here is I have chosen this as an id, that's my terminal. Okay, and then star, now this e goes to id. That means now this e goes to id as a terminal. Then plus and e, for this e I choose now the id, and now this goes to the id. Okay, in the leftmost way I go, that's called leftmost derivation, where I choose to derive the leftmost variables to the terminals. Okay, now I got id into id plus id. This is what I was searching for, and I got the string from this grammar. So I say, yep, I got the parse tree for this particular grammar, for this particular string. So I'm able to say, yep, this string belongs to the language pertaining to this grammar, right? Now I could have done the same thing using the rightmost derivation. Okay, if we try to do this with the rightmost derivation, before that I must say that if we do the in order traversal of the leaves, that will give the original input, that is this thing. Okay, here, this thing. So in order traversal, if you do, okay, in order you must be knowing from the data structure, then this will give you the original input. Now for rightmost derivation, what you do is you will have the same thing. Say for example you have e, you start from the start symbol, then you use for example e plus e. Now you in here we started deriving this e, but here we start the rightmost, so that's called rightmost derivation. So I will say this e to the id. Now this goes like this. Now I choose this one to make it as e star e. Okay, and plus id, right? And same way I go further the right way to make it this guy as id. Now this is id already done, so into e. Then I go this one and convert this into id, id into id plus id. Now this is the rightmost way of doing things. This will be the same. The firstly e, then make a 3 kids of the e, then convert this to id. This remains same. Okay, then this e goes to 3 things. One is star, one is e, and another is e. Then this one goes to id. Then at the end this one goes to id. So the parse tree we have is the same as above. Okay, they are the same 2 parse trees, right? Or derivation trees, what we can say, which have the as a terminal as a leaf nodes, right? So you can say this is the rightmost or leftmost derivation. Only the thing is that which part you started deriving first. Okay, right part or left part. Let's take up another example to understand it properly. Okay, say for example we got a grammar e plus e, e asterisk e, e, and we got also the minus e. Only difference here is we got also the minus e in this. Right here we didn't have the minus. Okay, in this we had a e plus asterisk e and id. In the parentheses, this is same as here, but only once we have one added thing here, that's minus expression. Now we want to find is minus id plus id in a sentence in this grammar or not. A sentence in this grammar or not. Okay, a sentence, we know what it is now. That will be the, like here the sentence is this guy, id into id plus id. Now is this sentence in the grammar or not? So what we do is we can use the derivation tree. We will build a parse tree and see if it is, the parse tree is built, and we could make a sentence or a parse tree, and we say yep, it is, it belongs to the grammar. So the answer is yes, because we have a following derivation. So we say use firstly e, okay, and instead of e, and then we derive it to this rule minus e, okay. Then this rule minus e to this rule, from because e inside, so minus will stay there, and this e will go to parentheses e. Okay, now this e will be derived or it gives this by using this derivation rule, e plus e. So a minus stays there in the parentheses. From this e we derived e plus e. Okay, now we change this e to I using this rule id, and this e goes to id. So that means minus id plus id, yes, it is there. Now let's examine it, the derivations here, right? This is the same thing. Now we could build a parse tree. The firstly that we have a e, then two children minus and e, then parentheses, okay, with the e. So e will have three things: minus, parents open, actually four things now. Minus will go here, then this e will have the left parent, e and right parent. Then we expand it, this e, now this e is expanded to e plus e, okay, and then giving the IDs. Okay, so this is also the top-down derivation. As we could see, we started from the root and goes to the leaves, right? Now parse tree actually is a graphical representation of the derivation sequence, and it has in the leaves, as a leaves it has the sentence, and if it belongs, it matches to the sentence we are talking about, we like this string, and we say yep, it belongs to the grammar.